Thank you. Awesome. Thank you for the invitation and given your interest. So yeah, I'm talking about polytopes, periods, and degenerations. I have some videos at the beginning of the talk, and they only play if I'm not in full screen. So don't be surprised that it's not full screen. The first few slides I have to go through like this. It's not perfect, but somehow it doesn't work that way. So what you see here is a plot made with Surfer. It's an app that I like from the Imaginary platform. And you can put in an equation and make little videos even with parameters. And what you see here is a Quadratic surface, of course, a real plot in three-dimensional space. So it's given by a polynomial with 3 variables and is of degree 4. So it's a Quadratic, and Coma studied this Quadratic, and he studied this particular degeneration of a Quadratic, where you see then it acquires 16 nodes. See the nodes here. If you count them, there's there are these 4 little tetrahedra that you see, and each of them has 4 nodes, and then some meet each other. So it should be 16 in total. And this is known as the Coma surface, and these surfaces with 60 nodes. There are many different ones, can look very different. It's quite interesting to look at all of them. But today we want to do something else. So this is called the degeneration. Maybe I should say that. It's the first term in my title that I'm introducing, degeneration. And we want to do even more serious degeneration. So what you're seeing here is starting with the same smooth surface, but now we degenerate really seriously so that it breaks up in a way which makes it look rather different. It's now simply a union of 4 hyperplanes. Okay, so what I've done with the equation, I'm not showing the equation to you, but what of course happened is that you deform the equation, which was a degree 4 polynomial, so that it deforms into a polynomial that factors into 4 linear factors. Then you see the 0 set of each linear factor is a hyperplane. And that's how you get this degeneration. So you deform in a pencil, and then it degenerates this way. So I'm interested in degenerations that are as serious as this one. Really, we can call them maximal. You break it up. And the advantage of these breakup degenerations, which are so serious, is that they are more combinatorial. Okay, I think now I can go full screen. Try to do this. Okay, now back a little bit. Oh, so that was too fast. I'm still getting used to this. So as you saw, we have degenerated basically a Coma surface or a Quadratic surface into a tetrahedron, roughly speaking. So it was in the union of 4 planes, and you saw the tetrahedron in the middle. So my point is that when you degenerate more seriously, the thing becomes combinatorial, and you have some combinatorial dualities on polytopes. That's the next notion in my title. So here you see a bunch of polytopes, and you're probably familiar with the notion of polar duality for polytopes. You see on the top row a tetrahedron, a cube, and a dodecahedron. And if you perform the following, if you put a vertex, a point, in every facet, so every of these faces of the polytope in the top row, you put a point and then take the convex hull of all these points, so 1 point for each facet, then you get the polytope in the bottom. This is called polar duality. So the polytopes in the bottom have as many vertices as the top polytopes have faces, top faces, facets. Okay, so this is polar duality. It's fun to play around with this, a nice combinatorial duality. And we want to combine this with the previous story of degeneration. Okay, and this has a very natural framework where this shows up, probably also in other contexts, but we're interested in mirror symmetry at this point. Mirror symmetry is something about Calabi-Yau manifolds, at least originally, and Calabi-Yau manifolds are, for instance, Coma surfaces. That's fine, but also higher dimensionals. And of course, you probably all know that the Coma surface more generally is called a K3 surface. So Calabi-Yau manifolds are higher dimensional versions. So we go from dimension 2 of a surface to a 3-fold. And in the early 90s, mathematical physicists performed this plot where you see here that when you look at all Calabi-Yau threefolds that were known at the time, they came as hypersurfaces in weighted projective spaces. So all these Calabi-Yau threefolds they looked at because they needed them for physical studies or for theoretical physics. They plotted two characteristic numbers of all these Calabi-Yaus, namely the Euler number, that's on the x-axis, the horizontal axis, and then basically the total rank of cohomology goes on the vertical axis. And so every Calabi-Yau that was known at the time is represented by one point in the diagram. So you see here a nice pattern of all kinds of points, many, many points. You see there are lots of them. I think there are about 7,555 dots in the diagram, if I remember the number right. And what's most striking, of course, is that this has a nice pattern of symmetry. In fact, it has many patterns, but the most striking one is the vertical symmetry along the vertical axis, if you mirror that. And that's why this observation that there is such a symmetry, looking at the diagram, is called mirror symmetry. It's a mirror duality at this axis. It's a reflection symmetry. So yeah, that's called mirror symmetry. So what's behind that? So it means that there's a relationship between different Calabi-Yaus, because different dots that you mirror when you on the vertical axis, they correspond to different geometries. Barterev discovered that a mathematical explanation for this duality can be found in polar duality. So you just think of that each of those dots, each representing a Calabi-Yau threefold, is a hypersurface in a toric variety. It was a weighted projective space, but you can also generalize it to more general toric varieties. And then you just perform a polar duality of the polytope that describes the toric variety. And then you get another toric variety. Inside is that is also a hypersurface, which is a Calabi-Yau. And that's the mirror dual point. So these 2 points are related by both of them being hypersurfaces in a projective toric variety. And then the projective toric varieties are related by this polar duality. That was a discovery in the early 90s. So that's quite nice. But there's a lot more to it. So this only apparently, as you see, it only works for hypersurfaces in toric varieties, but Calabi-Yaus can appear much more general. Not every Calabi-Yau needs to be a hypersurface in a projective toric variety. So we need to generalize this construction, and there's an interesting geometric interpretation for it, which was suggested in 1996, namely that two Calabi-Yau threefolds, whenever they are mirror dual, but so have this relationship, they should fiber over the same base, and then the fibers should be dual tori. Okay, so there's a completely different description. It doesn't seem to relate to this at all. It doesn't need a hypersurface. Calabi-Yau doesn't need to be embedded anywhere. The independent description or suggestion, it wasn't a proof or anything. It's a suggestion mostly how that should work. And of course, it's motivated from physics. Originally, this all comes from physics, and there are lots of other structures that are motivated from physics. And these were the first 2 attempts maybe to put it into mathematics. So these are fairly independent points of view, which then got unified by Ilya Zarkov and Gross-Siebert, where they realized that you can bring the polar duality together with the torus fibration. So for those examples that are hypersurfaces, you can also interpret the mirror symmetry for the point B. So the hypersurface polar duality thing becomes also a duality of torus fibrations. So Zarkov showed that in Gross-Siebert also. But in order to do this, you need to degenerate. Okay, so it brings us back to one of the things in the title. You need to degenerate your Calabi-Yau hypersurface, just like we did with the Coma surface in the start, in order to be able to see this torus fibration. And I'm going to explain next how you get this torus fibration from a degeneration. First of all, let's look back into a little bit of projective toric geometry. Every projective toric variety permits a continuous surjection to a polytope. So we're thinking of the toric variety as being defined over complex numbers, now a complex projective variety, and there's a continuous map to some polytope. Here's the example for CP1. If you look at the complex line, it's topologically a two-sphere. And it gets mapped down to an interval. Okay? An interval is a polytope. That's fine. And the fibers encircled, except over 0 and infinity, you see the pre-image at a certain point. But you have this continuous surjection. And the map is given in terms of an affine coordinate, as you see given here. So you use the absolute value, it factors through taking the absolute value, and then you perform this thing, so you end up in an interval. Okay, that's a moment map. And it works similarly for CP2. Here again, given an affine coordinates, looks sort of similar. Now what happens is CP2 is a real four manifold. That's CP2, complex plane, real four manifold. And it maps to a triangle surjectively. And most of the fibers are two tori. So you see here sketched over the interior points, you get a two torus as a fiber of this moment map. But on the boundary, you get a smaller dimensional fibers. So the general point over an edge, you have a circle, and over the vertex of the triangle, you just get a point, similar to the example on the left-hand side. So that's the moment map. And we need this moment map also for the Calabi-Yau's. So what we want to do is we want to use the moment map for the projective toric variety to now produce one for Calabi-Yau hypersurfaces. Okay, so here's a remark. Conversely, if you start with a polytope, like a triangle or interval or anything, you can also associate a projective toric variety. So there's a correspondence between projective toric varieties and polytopes. You can go back and forth between them. And the relationship is then always that the projective toric variety maps to the polytope by the moment map. Okay, so that's the story that we to use. Now we want to glue those kind of toric varieties together. If two toric varieties meet in boundary strata, we can glue them together, and we can also glue the moment maps to the polytopes. So this looks like this. Here I have a bunch of CP1s, 3 of them, and I glue them along the toric strata. So that means CP1 has 2 zero-dimensional torus orbits, that's 0 and infinity, and I can glue the infinity point of one CP1 to the 0 point of the next one. And so I can form a chain like this, where I glue one to the other, and then each of them maps by moment map to the interval, and I can also glue the intervals together. So you see that down here, so that in total, I get a continuous map from a chain of 3 CP1s to a union of 3 intervals. Okay, and I can form this more generally. I can glue toric varieties along boundary and then map to the glued polytope stuff. So this gives a map that I would like to study. So this is a dictionary. If I have a degenerate manifold, which is a union of toric varieties that meet along toric strata, for instance, this thing here, you can say the union of the 3 CP1s is a degenerate manifold. And so as long as it satisfies that it's consisting of toric varieties that are glued along toric strata, you can then associate to it a topological manifold where you glue it from polyhedra. You know, to be a topological manifold, it has to satisfy that along each stratum only 2 come together. So if I glue 3 CP1s along a point, that's not permitted. But as long as I glue only 2 at the boundary stratum, then you get a topological manifold from this, basically glue it properly. So we have this dictionary. You can go from degenerate spaces to topological manifolds, real manifolds. And we want to use this and enhance to a torus fibration. Now, this degenerate manifold is not quite a Calabi-Yau. This is because very singular. But what you can do, as in the beginning of the talk with the video, you can start with a smooth Calabi-Yau, like a Coma surface, and you degenerate it in a family to a singular one, which is then a union of planes. The union of planes, by the way, is an example here. It's a union of 3 complex planes which meet along toric strata. So you degenerate into exactly such a thing where it can then glue the moment maps together. So that's what I'm going to do. I have 2 steps in this process. First, I start with a smooth manifold, degenerate into something singular, the union of toric varieties that meet along boundary strata, and then I can use the moment maps and glued moment maps to compose that. So what does it look like in examples? Here's the example of the elliptic curve. In the elliptic curve case, so imagine the elliptic curve is somewhere, and we degenerate it so that it acquires a node. So you contract this green circle you see, the elliptic curve gets a node. And if you do this in a family, there's a retraction map from the smooth elliptic curve to the degenerate one. And then I can compose with a moment map. Now notice that here, this degenerate elliptic curve is a CP1, where I've glued 0 and infinity together. So it's an example where I glued something, I glued it to itself. And so then the moment map maps to an interval where I've then glued the endpoints, which is a circle. So you see that here I've applied the construction. On the right-hand side, you see the moment map. On the left-hand side, I use the retraction, and I always do this. So I compose the retraction map with this glued moment map. That's for the elliptic curve. And you see that the entire composition of these two maps is a circle bundle. It's a circle bundle over a circle, okay? But I can also do this in higher dimensions. Here's a K3 surface situation. I started with this smooth K3 surface, sketched here by its real picture, you see. And then I degenerated into the union of hyperplanes by a retraction map. And I can then compose with the union of these moment maps, which then maps to the boundary of the tetrahedron. It's important the tetrahedron is not filled, it's just the boundary. Because I'm gluing three triangles along the boundary, so that it becomes a two-sphere. Topologically, I'm mapping here a K3 surface to a two-sphere. Okay, and the fibers, the general fibers are tori, but then the interesting thing in higher dimensions, like the K3 surface already, is that some tori are singular. So we need to talk about singularities of this fibration. In general, this composition mu after R is called the topological Strominger-Yau-Zaslow fibration. So it is this candidate for what I said earlier. There was a suggestion that mirror symmetry is a T-duality, it's a duality of tori. Here we've constructed such a map from tori. It's just not a duality yet, but there's one space that has a fibration in tori over a base space. And it's a candidate for this fibration that we can then take a dual of to get the mirror dual Calabi-Yau. If the dimension is at least 2, there are typically singular torus fibers in this fibration. So in this K3 surface case, in the Coma surface situation, you can get an understanding where the singularities are. You just need to look at just before we have degenerated. This is a smooth picture, a smooth Coma surface, which is just before it has been degenerated. And what you see is that there are special points where, if you look in the movie, these are the points where the smooth guy intersects the single locus of the degenerate guy. These are actually 24 points. You can count them here. So that's just, basically, you can view them as kind of branch points. If you were mapping to each, the union of two of these 4 planes has a singular locus, which is the union of lines. So 6 lines. And along those 6 lines, you have these special points. And if you map then compose this moment map with the retraction map, then that's where you have singular fibers above it. So over each of those red points, which are the images of the points in the K3 surface, you have a singular torus sitting there. And we want to look at what that singular torus look like. But before I do that, let's do a bit of a generalization. Here I give you equations for the families where you deform your hypersurface in a pencil, then degenerate, and then what does it look like? What spaces do you get from gluing the moment maps, So here you see a bunch of examples. The first one is that we've seen already. Capital F4 just means it's a homogeneous polynomial in these variables of degree 4. Okay, so it's a quadratic polynomial, general enough so that special happens. And T is a deformation parameter. So when T goes to 0, then we have a degeneration into a union of toric varieties which meet in toric boundary strata. So on the left-hand side, you always see the product of monomials, which give the degenerate fiber. So if you set the left-hand side to 0, that's what the degenerate space looks like. And it's combinatorially seen on the right-hand side with these gray images. So these gray images are the union of polyhedra, which are glued in the boundary. And there's as many polyhedra as you have monomials on the left equation, right? So this is exactly what you get from performing this construction. You have this pencil where the variety for T non-zero is a smooth hypersurface. Here it's in a projective 3 space because we have 4 homogeneous variables. And then when you send T to 0, you get the union of coordinate hyperplanes. So union of toric varieties meet in boundary, and we can perform this construction, retraction map to the central fiber, and then compose with the union of moment maps. And what you get is the geometries you see on the right-hand side. So the first one is a sphere, and then the other ones are topologically just disks, right? So that's the difference. The first one is a Calabi-Yau, and the other ones are more like Fanos. That's why you get just disks and not spheres. But interesting is also how many singular fibers you get, what the discriminant is. So over each of the red points in these pictures on the right-hand side, there is a singular fiber in this family. And so the bottom one does not have one singular fiber, but what I should also say is that in the case where you have a disk, which are most of these cases, the boundary has a particular shape, which I haven't pointed out here correctly or entirely in all detail. So maybe you wonder why one of them has a singular fiber but the other not. So the difference in them is that in fact, I'm actually degenerating a pair. It's not just a conic. So for the last three equations, you see this is degree 2. I'm degenerating a conic. Quadratic. Conic is a curve situation. I'm degenerating a quadratic into a union of two planes. And it's actually a generation of a pair because over the boundary of my polytope, or the union of polytopes, there's also some stuff going there. And this is different for the cases. So in the bottom, very bottom, where you don't have singular fibers in the torus fibration, there are actually singular fibers over the boundary. And the boundary here is a union of 4p1. So each boundary interval has a p1 above it. And so that changes when you go to the one above. So the penultimate one here is the boundary is only 3 components. So you've sort of smoothened your boundary somewhat, but you traded it with singularities in the torus fibration away from the boundary. Okay, so the boundary also in the third to last one, where you have 2 singular points. Here the boundary is just 2 p1. So you have a quadratic with 2 p1s in it. And then you have a torus fibration, the complement of those 2 p1s, which has 2 singular torus fibers over these points. That's what you get from it. Okay, so what we do next about this is we want to look at special cycles in the nearby fiber. So the nearby fiber is a smooth manifold, and we have now this torus fibration that maps it to a topological manifold. In our examples we looked at was a sphere or a disk. And we can use this torus fibration to refer to particular cycles in X in terms of something that we construct on B. Okay, here I have a situation where I have 2 nodal torus fibers. So this is the situation what it looks like when you have 2 singular points on an edge in the intersection complex. And over those sit singular tori as fibers. And I can, if I have 2 of them, I can make a matching cycle, as symplectic geometers call that, where you looked at in between those 2 singular fibers, they're actually smooth torus fibers in this fibration. And I can then produce a sphere. That's the green thing I sketched upstairs. That's supposed to be a 2 sphere. It lives inside X and fibers over the green edge downstairs. And the green edge connects 2 singularities. So this is called a matching cycle, or yeah. So basically, if you're familiar with the vanishing cycles, I've taken 2 thimbles and glued them to a sphere for the vanishing cycles to the single points. So that's useful because I can now construct cycles in my space, singular homology cycles. I want to do a variant of this. It's a very similar cycle, but it's not quite the same. You see here. Here, I'm not going to the singular fibers. I'm basically staying away from them. And I'm producing a cycle that fibers over the goggle. You see downstairs in the base, there's this goggle object. It has 2 loops that go around 2 singular points in the discriminant. And they're joined by an edge. And upstairs, I actually have over each circle, I have a torus. And these torus are connected by a tube. So I get those kind of cycle I can construct. I'm basically making use of that there's a torus fibration. I understand the torus fibration fairly well, and then I can construct these cycle upstairs. Okay. And these 2 that you see, the one above is a sphere, and downstairs it's a more funnier thing. It's a genus 2 curve. These 2 cycles are actually they relate to each other because the difference is a union of fibers. Okay, you can see that the difference of the sphere upstairs, the green one, and the 2 torus, the 2 genus 2 curve downstairs, this green thing. The difference is 2 tori, basically. One has 2 holes and the other one doesn't have a hole. And so if you actually add 2 fibers, which are also cycles in the total space, then you get, these are different by 2 such fibers. So a modulo of taking fibers, which I'm going to do next, I'm working modulo the fiber. Fiber is always a cycle. I'm not so much interested in that one. Modulo the fiber, these 2 are actually the same. Okay, here a bit more general. If you look at this space that I constructed from gluing polytopes, it has a discriminant. That's where we have singular torus fibers. And there's an integral affine structure in the complement of these singularities. Okay, so because the torus fibers have, you can take the local system of homology, first homology of the torus fiber, that's a z to the n local system, call that lambda. And it's a local system away from the singularities, and this local system has some monotony when you walk around a singularity, but it gives you an affine structure on the complement of the discriminant. And now I can embed this open complement of the discriminant into the entire topological manifold. I can push forward this local system as a sheaf now, and it's a constructible sheaf. The rank will drop. So it's away from the discriminant, the rank is always n because of the first homology of this torus fiber, with the always nice tori above it. But then when you go to the singularities, you get a lower rank. It's only that rank that's invariant when you walk around from a singularity. So I'm using this local system of the first homology of the torus fibers as a local system on the base to construct these cycles. So here's a definition. A tropical 1 cycle in the base B is a singular 1 cycle just for singular homology. Let's call it beta trop, but with coefficients in a constructible sheaf, namely this I lower star lambda. If your support of the cycle is away from the singularities, as it is in the picture you see on the right. So here I have my K3 dual intersection complex I got from the degeneration. I have a green cycle in there that doesn't meet the discriminant, so it's away from it. You can then say it's a singular chain with coefficients in the local system, because this I lower star you don't need to do. You don't need to push forward for this one. It's just a local system, and you can have singular change with coefficients in the local system, right? The common thing in topology you can do. So I'm looking at these 1 cycles with coefficients in the local system. It means every edge of the cycle has a section of this local system attached to it. And when edges come together, these sections need to add to 0 with the orientation of the cycle. Okay? Just like what a singular chain is with coefficients in the local system. And the associated homology group I call H lower 1. Okay? H lower 1 is this homology group. There's now a natural homomorphism from this homology group of 1 cycles into the ordinary middle dimensional homology of the nearby fiber. So remember, the smooth manifold maps to this base. We can take these tropical 1 cycles in the base, and we can map them to actual cycles in the smooth total space. Just like what I did in the slide before, where I started with something in the base and I could produce something that fibers over it. There's a general procedure for doing this, that I start with a cycle in the base and associate something in the total space that maps to the thing in the base. And I always have to mod out the fiber of the fibration. So that's what you see here. It's only well-defined my construction up to adding multiples of a fiber. So in this previous case, I would consider those 2 cycles the same, the sphere and this genus 2 curve, because they differ by 2 fibers, which you don't see easily. This is an analysis you need to make, that they're actually related by just adding fibers. But I always want to kill the fibers and then look at what's left after doing that. And the map I call beta trop goes to beta. Okay, so beta trop is my green thing, and the beta is the actual thing in the total space, the nice, with the sphere or the genus 2 curve that we saw in the previous example. Okay, so what can I use this map for? Well, first of all, as you can see, there's a relationship between these tropical 1 cycles and actual cycles in the smooth total space. So it might be interesting to see what the ranks are. So how many cycles are there when you choose a basis for the homology? And here you see the ranks in these examples. So the first one was the K3 surface, the Coma surface, and you see that this 1 group of tropical cycles is actually 20-dimensional, which is a number that is probably familiar to when you know K3 surfaces, because it's the middle Hodge number, H11. So it seems to fit very nicely here that this is indeed a Hodge number of the K3 surface that you see as a rank for these tropical cycles. And if you do the other ones, you see that the rank is lower. mostly because there's not as much stuff you can walk around. So I'm constructing these cycles basically in the similar way that you saw with the goggles. So I'm using some singularities, I walk around them, construct some cycle from that. And the fewer singularities you have, the less many cycles there are. And you can compute the rank here. So it goes down to 7 and 4, and then eventually 0. If you don't have only one singularity, you can't actually make a cycle of that one. And 0, yeah. So that's what it looks like. And we're going to use these cycles to come to the final term in my title, which is period intervals. We'll do that in a moment. But let me first refer to an interesting duality that we have with these local systems. So I said that lambda is the local system of first homology of these torus fibers, which is local system away from the discriminant. And I can take the dual local system and just do hom to z. It's a dual. So I have dual local systems. And the interesting thing is, dual local systems have a nice pairing, of course, and that's not so fantastic, or it's not so surprising. But if you push them forward over the discriminant, then things can really be different. So now, when you push them forward, these are just constructible sheaves. And here I'm producing a pairing between homology and cohomology. It's really just a cup product pairing, cap or cup or whatever, one of these. And but the thing is that you can do this with push forward. Okay, that's less obvious. That you can have a pairing with push forward. If there wasn't a push forward, if you just work away from the discriminant, that's kind of obviously such a pairing. But it works also with push forward. And this pairing is perfect if the discriminant is not too bad. So if the discriminant is simple, which is actually true in all our cases that we looked at, but let me give you a bit of an idea what simple in general means. If the dimension of the base is 2, like the examples we looked at, then that you can study the monodromy that you have around a singular point. It basically should be a Dehn twist. So it has this shape. It's this matrix, which is a shear matrix for some k. If you're in dimension 3, which I haven't looked at yet, but then the discriminant is one-dimensional. It's in fact the way you construct it here, it's even bigger dimensional, but it retracts to a graph. Okay, so in dimension 3, the discriminant retracts to a graph. And the graph has vertices. And if my graph is trivalent, then I'm in good shape. So I'm asking my graph to be trivalent, and then around each edge in the graph, the discriminant should basically, the monodromy around the discriminant, or around that edge, should be just of the type of the two-dimensional case times an extra trivial direction. Okay, so that's what simple means in dimension 3. But here's also an easy way to break it, namely, if you have, say, a 4-valent vertex in your discriminant, then it's immediately not true that this pairing upstairs is perfect. And this reflects that you're actually looking at the geometry of a conifold. When you have a 4-valent vertex, your Calabi-Yau that you started with is a conifold. And for instance, Poincaré duality doesn't hold true for that one. That's reflected here in these tropical cycles, that the pairing here is also not perfect. Okay, so this perfect pairing is very useful because it helps us to show that this map that we constructed, the homomorphism that goes from the tropical 1 cycles into the ordinary cycles of a total space, is injective. Okay, so you always have to mod out the Z fibers and its multiples. But when you mod that out, then afterwards this map is injective. So it's pretty cool. So we actually know that those, that's embeds in there, and we get a subgroup of this homology of the total space from the tropical 1 cycles. And for instance, in this example, where I had this goggle that looks like a genus 2 curve upstairs, it is actually a generator. Remember, in my list of ranks of the spaces, if I do the thing where I degenerate a quadratic into 2p2s, and I do that in this way, given by this equation here, then I have this map is an isomorphism over Q, and both things have rank 1. So the tropical cycles have rank 1 is generated exactly by the goggle and its multiples, and it maps a priori it maps to H2, but it actually maps to H2 of the complement of this boundary divisor D, and it generates that. So this H boundary divisor H2, so X minus the divisor D. If you then kill the SYZ fiber again, that has rank 1. Okay, it's an isomorphism with this H1 downstairs. There may be torsion, but after tensoring with Q, it's an isomorphism. And we know this from the pairing, so it's kind of very useful to have this pairing. Now, let's go to the final notion in my title. Let's talk a bit about period integrals. Let's have an elementary start at it. A period integral is an integral of a homomorphic differential n form on a complex manifold X over an n cycle beta. We already see where it's going. We want to use these cycles we constructed just before and now integrate over them. Integrate a holomorphic volume form. If you're on a Calabi-Yau, there's a natural holomorphic volume for up to scale. So for instance, an elliptic curve is a Calabi-Yau. Here you see it represented as a quotient of the complex plane by a lattice with parameter tau. On the right-hand side, you see the fundamental domain. And so what you do is you get this elliptic curve by gluing the opposite edges of this fundamental domain to each other. And then it becomes this two torus. And as you do that, you naturally produce some cycles here, namely the edges that you've glued to each other then become actually circles on the elliptic curve. And these are actually some of my circles I'm constructing. So you can use this beta downstairs is actually a valid tropical cycle. There are no singular fibers, but still you have these cycles in the base. And you can use them to produce cycles upstairs. Here it's kind of a little bit boring. So the beta downstairs in my, actually I haven't said what the torus fibration is here, but yeah, it was in another picture. Anyhow, let's use this beta, which is just a circle, and integrate a homomorphic volume form over it. The homomorphic volume form we take is just dz. It's just the ordinary form that with the standard coordinate on the complex plane, just take the form dz, so a global volume form on C, it descends to a global volume form on the elliptic curve, and we can compute the integration of that along this cycle beta. This is a closed integral here on the left-hand side, by just lifting it to the fundamental domain, and then it becomes integral from 0 to tau, because now the circles are breaking up, and you go from 0 to tau and integrate this thing, and it has a antiderivative easily, just z, it's inserted, and you get tau. Okay, so we learn from this calculation here that tau, the parameter of the lattice, is a period, okay, for this volume form. And we want to generalize it and study more of those kind of periods for other cycles. Yeah, that's what I said before. Calabi-Yau manifold has a unique differential form, so we always know what form to integrate. And we've spent a lot of time already constructing cycles, so let's just do it. Integrate this natural form over all kinds of cycles that we've constructed. But before we do that, let us study what happens if we deform the elliptic curve, so degenerates. That's another thing we do, degeneration. Here's a way to do this. You take the elliptic curve and you map it on the exponential map to obtain a different representation of it. Now, previously was a quotient of the complex plane modulo a rank 2 lattice. If you apply the exponential map, you've basically taken care of one of those factors of the rank 2 lattice. And then it becomes a multiplicative quotient of the complex plane minus the origin, that's C star, modulo a cyclic group, which is generated by T, and T is the exponential of 2 pi I, tau, 2 pi I tau. Okay, so the parameter that was tau in the lattice before now becomes this generator of the cyclic group, cyclic subgroup of the multiplicative group of the complex plane. And you take this multiplicative quotient, and then you also get the same elliptic curve. This is an isomorphism. Okay, so here, nothing fancy happens, just a different representation, turning this T into, basically we've gone to exp of tau. And this T is an important thing. It's a canonical coordinate, as it will show up later in the game as well. So what we're doing, remember summarize, we take an exponential of 2 pi I of a period. Tau was a period, remember that, right? So we'll do that a lot later on. Take an exponential of 2 pi I of a period. Okay, let's study what happens if we degenerate the elliptic curve like this. You see here, I have a smooth elliptic curve for T non-zero. And I can't really form this quotient when T is 0, right? If T is 0, I don't get a cyclic subgroup of C star. But you can actually fill in something there. Pretty naturally, you fill something over 0, which has to be a nodal curve. You can see from the nearby fibers that something has to break there, and you get a nodal. This is a degeneration of those kind we looked at before. So you fill in over T equals 0 this nodal curve. That's also why I did this different representation. I went from the elliptic curve to this Tate curve, as it's said. So Tate curve when you do this multiplicative quotient, because then I can go with T to 0, and that is what I fill in then this nodal curve. t going to 0 is the same as going imaginary part of tau to infinity, okay, if you want that correspondence. So I have this node curve in the center. What happens with my period integral? Where does the period go when t goes to 0? Well, that's just because we've already computed the period, we can say exactly what it is. So the period, remember, was tau. So if t is my parameter now, to get back to the period tau, I have to take logarithm of t effectively. Okay, 2 pi I is maybe missing, I'm not sure. But the period integral is the logarithm of t. When t goes to 0, you can't evaluate that, right? Because the logarithm has a pole at 0. But that's just what it is. So we learn that it's always, actually, well, most of the time the case, that when we move a period into a degeneration, it requires these log poles. You see perfectly here. The general story, now from this example, we go to full generality now. It's a theorem that I worked out with Siebert together. We have the entire setup we talked about. We have a degeneration into union of toric varieties that meet a toric boundary strata. We can then construct this topological SYZ fibration over this manifold B. And we can use tropical 1 cycles in the manifold B to construct ordinary cycles in the manifold we started with. And we then can start doing this integration for them. And we found a very simple formula. So the period integral over the cycle in the manifold that's associated to a particular tropical cycle follows this formula. What I'm doing here, I'm using the standard holomorphic volume form omega. That's any Calabi-Yau has that one naturally, and also the other spaces where you did non-Calabi-Yaus in the examples. Those was log Calabi-Yau, and also log Calabi-Yaus have a natural form. So this form is always around. I'm integrating over the cycle that I get from a tropical cycle. I mod out this factor in the front. That's not so important. But the interesting thing is it has 3 terms as integral. One term is of a kind we just saw already for the elliptic curve. Just gets an integer factor in the front, kappa. And kappa is the number of crossings that this tropical cycle has with the codimension 1 walls in B. So here, when you look on the right, this green cycle crosses the black stuff, the black codimension 1 polyhedral loci in a bunch of points. And you count how many, and you count also with signs. And that's the factor in front of log t. And the factor can well be 0, because they go with signs. So some cycles may actually have none of these log t term, and then they're holomorphic. Okay, so this front thing is the non-holomorphic part. This log t has a pole in 0, and the rest is holomorphic. It's very important. And then there's a gluing term and Ronkin term. I could say more, but I'd rather talk about the applications of this. So these are very explicit terms, which are easy to compute. So it's a very useful formula that have this easy formula for these period integrals. Okay, so here's an example of that illustrates this general theorem in an example. This is like the degeneration of a quadratic surface in CP3. So we fixed 2 parameters A and B in the complex numbers, and then we look at this affine equation. But you can view it as an affine equation that belongs to a degeneration of a quadratic that we had before. And there are 3 variables now because we're affine. In affine 3 space, the 3 variables are x, y, and u. And u is invertible, so we removed u to 0 from the space. And what you see here is, it's an equation in x, y, and u, and a and b are constants, and t is the family parameter. So we have a family of surfaces that degenerates to a union of 2 affine planes, or when t is 0, the entire right-hand side vanishes, and then I have just x times y equals 0. So it's the union of 2 hyperplanes, so something like what we looked at all the time. And if it's t is non-zero, then you have a smooth surface as long as a and b are not the same. Then it's a smooth surface. So we degenerate a smooth quadratic into a union of 2 planes. And how do we do the period here? Well, the picture is like this. This is exactly the situation that we had pictured before what the torus fibration is. The affine manifold now has 2 singularities, which are the zeros of the 2 linear factors you see on the right-hand side of the equation. So these are now the red points in the base. The base consists of 2 polyhedra, if you like. If it's compactified, then you have 2 polyhedra that glue along an edge. And on that edge, you have 2 singular fibers, these red dots. Torus fibration over it, 2 singular fibers. And I make this goggle that I've done before. So here it's just in the base, but upstairs, you know, there's this genus 2 curve above it. And I can now integrate my cycle over this green thing. As I said, this green cycle comes with coefficients in the local system. So it naturally has these vectors along its edges because it's a cycle with coefficients in the local system, and they're sketched here as blue. Okay. What I've done, I've chosen a basis for the vector space. I've embedded this in a vector space. Then I only can represent this affine manifold with a chart. And I need to remove something. I've removed this dashed edges. You see the dashed loci, which are not part of this embedding when I want to embed this in R2, because the singularities you can't embed in R2 as an affine manifold. But if you remove some stuff, you can do this. So I've embedded this R2, removing this dashed edges, and then the green cycle sits here. And the matrices you see, they are telling you how to glue the top to the bottom by which transformation. So you see the transformations were just reflecting that there are these two singularities, and the red dots were singularities. And they are of this type 111. So that's the simple type. And they preserve the horizontal axis, these singularities. And so the interesting thing, you have to attach sections to the local system because of the monodromy. When you walk around this circular part, say on the left-hand side, then the vector changes when you cross the dashed part, because then you apply this monodromy transformation. And so the two endings of a circle, you have different sections, right? Interesting. So because of the monodromy, when you walk around, the section you started with becomes different. It gets sheared by this matrix. And then when you take basically the boundary map in homology, then you get the difference of those two sections, and that you can pick up with this other part of the cycle, which is the interval between them. That's how you get a cycle, right? So the difference has to be picked up by some other term to cancel out to zero. That's the middle thing. That's why we use a goggle, okay, to get that cycle. And the period integral for this is given by a formula that only depends on the intersection points, the orange points. You see 4 orange points here. You intersect with the codimension 1 polyhedral locus. And for each of those, you get a term that contributes, and only 2 of them contribute. The one in the middle do not contribute, the 2 terms. By the way, the entire period here is a ronking thing. It's exactly a case where this log t is a 0, the coefficient is 0, because we cross the codimension 1 locus 4 times, but +1, -1, +1, -1 with sign. Okay, so these 4 crossings that contribute to the period integral, they cancel out. So the number that was kappa, the number of crossings, is actually 0, because with sign, it's 0. And the only contribution we get here is from the ronking term. I've explained that properly, but it has something to do with the coefficient of this factorization in linear factors that you see upstairs. And you can show that the period integral over this green cycle, which was a genus 2 curve topologically, is just a times b. Okay, so you take the canonical form, you mod out, here n is 2 in this case, you mod out this factor and then exponentiate, and you just get the coefficients of the polynomial upstairs. Of course, I've put it in the shape, so that's kind of nice that you see it. Again, if your polynomial upstairs was not in this shape, you first have to put it in the shape to see what exactly the integral is. But so there's a very simple formula, that's what I'm trying to show here. It's a very simple formula how you can simply compute these period integrals. Even period integrals in general are really hard to compute. So if you move now, it doesn't depend on t. We're also interested. Okay? This doesn't depend on t, but other period integrals may depend on t. It's just the nature of this one, where you have 0 crossings if you count the sign. So these period integrals have turned out to be really useful for the study of mirror symmetry. Let me report about the work that appeared in Annals by Gross and Siebert. Here we do exactly what I told you about all the time. So we take a Calabi-Yau, we degenerate, or we start with the degenerate one if you want. And it comes with this base, the gluing of the polyhedra B. And we say that the discriminant is supposed to be simple. I explained that before, what it means roughly in low dimensions. And they prove that if you start with this B with a simple discriminant, you glue the projective toric varieties that are encoded in B, and you can smooth the thing. So this is like a reverse procedure for reconstruction. You don't need to start with a smooth nearby fiber, but you can start with a degenerate one and you smooth it. And that's very important if you want to do mirror symmetry, which is this duality where you may start with one Calabi-Yau degenerate, and then you use some kind of polar duality, which is called this Degeneration transform, and you get another one, and you want to smooth it out. So this is really needed if you want to construct a mirror dual Calabi-Yau, because then you need to smooth something. And that's happening here, where they show that there's a canonical family, a formal family, however. So it's over this base ring. I'm giving you the base ring, and you see it uses things that we've already looked at. Here it's not a homology in cycle, it's a cohomology. Okay, we can do that as well. In the dual local system push forward, and then it's a dualizing here again. But roughly speaking, it's a first cohomology of this tropical stuff in the base. And this group that you see here is just a free abelian group. So we're taking the monomial ring, the algebra over a free abelian group, which is the Laurent polynomial ring. So the first part is the Laurent polynomial ring, and then there's a t variable, which is formal. So we have formal in the t variable, and the coefficients are Laurent polynomial ring given by this cohomology group at the base. So then they naturally construct this family, and now we can compute periods for this particular family. And the first observation is that the Ronkim term vanishes. So we only have the log t part and the gluing term. And those correspond exactly to the two things that the base ring is decomposed of. So I said that there's the Laurent polynomial part, which is the first part of this base ring, and there's a t variable. And these are exactly the two things. I'm not sure how I can go back here. Let me not try, maybe later. So first was a log t term, and then there's a gluing term. These are the only things that you have, and they correspond to those. Let me explain exactly how. So remember there was this pairing, which you see at the very bottom line here, where you pair the tropical cycles, homology cycles with this cohomology, and it was a perfect pairing over Q in this setting, in fact. But it doesn't matter that's perfect for this point. Whenever you have a pairing, you can also view this as a map into the dual of the second thing. Okay, so you pair two things. It's the same as having a map from the first one in the dual of the second, same datum linear algebra wise. So we get a map from the tropical homology cycles into the dual of the cohomology, which is exactly the thing that is giving you the base monomials here for this canonical family. So in a sense, our tropical cycle group naturally maps into the monomials that are here in the base of this Gross-Siebert family. Okay, so that's kind of interesting. And then the following happens. Now we compute this period integral with the formula I just gave in the previous slide, and it becomes very simple if you use the pairing. Okay, so here you look at, if I exponentiate, of course, the log term, log t becomes then t to something power, right, log t, and the power is kappa that I had before. There was a number of crossings. But here's a way to compute this number of crossings. It's given by a pairing of the tropical cycle, which is the exponent of the t here. And this number of crossings is a pairing of the cycle with C1 of phi. I haven't explained that to you what C1 of phi is, but it's basically the codimension 1 stuff. So it's a class in this group, which is used to construct the smoothing. It's an input datum. So this is just the exponent kappa as you see here. And then there's a second factor, which corresponds to what was a gluing term in the sum of the integral. And it's just the monomial given by this tropical cycle. Right? So it's a very canonical thing. So you map the tropical cycle over in this dual, which is then, the monomial in the base ring that the family is constructed over. So this period integral is a supernatural expression. It is a monomial expression. That's an important thing. If you look at period integrals in other contexts in algebraic geometry, the typically hypergeometric functions, very complicated series. Here, the period integral is just a monomial. And that has to do with the very special nature of the family constructed by Gross and Siebert. So basically prove that this family is parameterized in canonical coordinates, which is exactly these expressions x of the period are canonical coordinates, and they give you monomials.
Sorry, how did you choose the holomorphic volume form again? Because it's only defined up to scalar normally. Yes,
that's right. Good point. So there's something I haven't said. So there was always say something about the SYZ fiber, right? We've always killed the SYZ fiber. We actually use the SYZ fiber. It's a natural cycle that lives in our family and the nearby fiber, and it contracts to the special fiber to fix the homomorphic volume form. True, the homomorphic is defined up to scalar. If you have a family, however, you can scale every fiber basically polymorphically around, but we fix the scalar by saying that the integral over the vanishing cycle, which is the S by Z fiber, is constant.
I see. Okay.
That's how I fix it. Yeah, thank you. So it's a good question.
Thank you.
Yes. So this is sort of a very natural expression. If you express it in terms of the pairing, then you get this period monomial. So it's kind of a new term. You can say it's a period monomial, exponential of a period. And then there's some really useful consequences of that. So we proved then using this observation that this formal family that Gross and Siebert produced in their work is actually a semi-universal. So it's a patch of a moduli space, you can say. It's parameterized in canonical coordinates, which I just said, which is Hodge theoretically really relevant. And it elliptifies also with these coordinates. So these coordinates that in Gross-Siebert's work were just formal, they actually natural extend to analytic. So you have an analytic family now that formalizes to the previous formal one. So it's also useful for if you want to do like actual, have an actual manifold, because previously the thing wasn't a manifold. Now you can take the actual holomorphic nearby fibers, have complex manifolds. Let me go back a little bit into why this is meaningful for mirror symmetry. In mirror symmetry, I started out with showing that these diagram with the Hodge numbers in all of that, and there's the symmetry in the vertical axis, and it means that some Hodge numbers of two Calabi-Yau's are equal. And you can translate it directly into this equality. If you have a mirror pair of Calabi-Yau's x and x check, then these Hodge number duality means that the first Dual group H1 of omega x, and omega x is the holomorphic differentials on x, that this is isomorphic to the first cohomology of the dual, but where you take the sheaf of derivations. So theta here means the sheaf of derivations. Okay, so this isomorphism follows from these Hodge number equalities you would observe in general. And we can now lift this to a higher meaning. It's just isomorphism vector spaces. But first of all, the isomorphism becomes canonical, and it translates these structures that these vector spaces represent. Namely, one of them represents deformation of complex structures, which is the right-hand side, and the left-hand side has the Kähler parameters. The Picard group has a lot to do with this. Okay, so here is how you get this canonical isomorphism. The versal Gross-Siebert family that we just mentioned is actually literally defined over this group on the right-hand side, because there's a canonical isomorphism of this first cohomology of theta with the C tensor of this cohomology group that is coming from this local system. So you can relate this theta group with the something on the base B. Okay, so there's a canonical isomorphism like that. So you can say that the Gross-Siebert family naturally parameterized over T1, which is the tangent space to deformations. It's naturally parameterized over there. And that tangent space has natural linear coordinates, right? Because a vector space has natural linear coordinates rather than general complex manifold. And then we have the match of these linear coordinates with the linear coordinates you have in the Picard group coming from the left-hand side. So that's basically what we prove having these canonical coordinates. Now, if you do this discrete Legendre transform, which is a generalization of the polar duality, then you can construct the mirror dual family by the smoothing result of Gross and Siebert. And you have this canonical isomorphism where this Dual group H1, which is up here on the left-hand side, equals this group coming from the affine base. So you have also this other torus fibration on the other side, and you can represent the cohomology of the holomorphic differentials in terms of this local system on the base, and you have to tensor by C, this canonical isomorphism like that. So now we've matched not only the dimensions, but we have a canonical isomorphism between the spaces, which is really one of the key things in mirror symmetry. You relate the Kähler structure, the symplectic structures who live in this Dual group, with the deformation of complex structures, and even with the coordinates on those spaces. That's naturally identified. Okay, so that's one of the key points. I'd like to thank you for being so attentive listeners.